So now we're ready to talk about how all of these things depend on temperature. So we, like with many other reactions, have been saying that something is just at a specific temperature, but you never really needed to use it, or we're saying it's at some given temperature without specifying a temperature. Well, the reason for this is that K is only a constant at constant temperature. So we have an equation that will let us calculate what the rate constant would be at different temperatures. Now, it just has some extra pieces that, of course, we have to define and set up for you, but I'm going to start by giving you the equation, and it's something called the Arrhenius equation. You probably recognize the name from acid-base definitions. This is just not going to look like anything from acid-base chemistry. So the rate constant, right, it's still our lowercase fancy k, is equal to a capital A, which I'll define for you in a second, E, as in the one that goes with natural log, and the exponent for E is negative capital E sub A, divided by R times T. All right, so the things that we have going on here, K is still the rate constant. So this calculation will let you, or this equation will let you calculate the rate constant. A is something called the frequency factor, which we'll define for you in a little bit with some examples. Usually you're given the frequency factor. E sub A is something called the activation energy. R, it's still a gas constant, but we're going to put it in with all of these energy units. So it's 8.314 joules per mole Kelvin, which, just a heads up, right? If your R value is in joules per mole Kelvin, and you're up here with the activation energy, you got to watch the units between activation energy and your gas constant. And then T is the temp in Kelvin. So what we're going to do next is define a couple of these things. I want to do activation energy first because we need to talk about another type of graph. So activation energy, this E sub A, it's an energy barrier. Or if you've learned about this before, sometimes we'll call it a hill that must be overcome to turn reactants into products. So the best way to show this is on a plot called an energy diagram. And so this is just a graphical depiction of energy changes in a reaction. So on our graph, I'm going to give you a specific type of graph here. Well, specific scenario for this graph. We're talking about how energy changes. So energy is going to go on what our y-axis is. And then this x-axis it gets labeled in a bunch of different ways. So a lot of times you'll just see RC, which means nothing to you at this point, right? So that RC stands for reaction coordinate. I mean, really what this is showing is the progress of the reaction. So that means from left to right, we're going from reactants to products, right? And the energy change that we plot should match up with that progress. So you can have reactions that have multiple steps and whatnot. We're going to start with just a reaction with one elementary step, and we will deal with elementary steps much more as we get into reaction mechanisms. But just so that you have kind of a good description of what we're going to draw here. Reaction with one elementary step. And we will see on here some information about where the energies start, where they end, and how, like what path it has to go. Because we've already said there's some barrier that we have to get over. We should see that barrier reflected in our plot. So what we have is that our reactants will be at some energy on here. Now, depending on when we talk about this, we may or may not have covered the thermodynamics chapter yet. If we have covered the thermodynamics chapter, this will mean a lot more to you. If we haven't, this is something that we're going to learn how to calculate as we go into a later section. So the reactants, as they exist together, have some energy. The products, as they exist together, have some energy. Now, the way that I have put these on here is not representative of every reaction. I've just put them on here like this so that we can show our example. And then as my reaction goes, it has some energy barrier to get over. So, let's put the top of my barrier somewhere like here. So the plot that I want to show is that from reactants, my reactants have to go up this hill, get over an energy barrier, and then as they turn into products, they'll end up at some different later energy. Now, the way that I have drawn this reaction, we would describe this because the products have a lower energy. A lot of people will say that the reaction is going downhill. You can have reactions that go uphill. It just so happens that this is an exothermic reaction because of how it traveled, but we've talked about endothermic reactions, even if we haven't done the thermo chapter. So the two differences that I want to label on here . The first, the difference between the reactants and the very top of the hill, this is the activation energy. So the value that ends up determining part of our rate constant is how big this hill is. So, and that kind of makes sense. If you have a really big hill, it will affect how quickly your reaction can get over it. If you have a really small hill, it will affect it in a different way. And then the difference in energy between the reactants and the products, this is a delta H reaction. So like I said, if we've done a thermo, you know what this means. If we haven't, this is the enthalpy of reaction. It just tells us how the energy of the products differs from the energy of the reactants, and it's something that we'll be able to calculate. And then a last little piece, the top part of this hill, I'm going to label this with something called a double dagger, which is just a straight vertical line with two horizontal lines through it. And that label is letting you know that at this point, we have something called a transition state. And it's just a high energy, partially formed product. So it's something that you see on the way. Well, you can't necessarily collect it and identify it, but it's something that exists. We have to get to this transition state in order to get the reactants to actually react with each other to turn into products. So we know now what the activation energy is. We're going to talk about the frequency factor and what it means in a little bit. But the question is really, how do we find the activation energy and the frequency factor? So where do these values come from? And then so that it doesn't look like I just tried to start a sentence and forgot, I typically try to label A as the frequency factor. So both of these values depend on the reaction being studied. But both of them can also be determined graphically. So the way that you would go about doing this, and you will not actually do this, but the way that this was derived is that, so we've already done these experiments and calculations to determine what the rate law would be, right? You run a bunch of trials and then get the rate law, and then you can use the rate law to determine the rate constant, or you could make one of the plots to determine the rate constant. Well, now we need the rate constant at multiple temperatures. So you would go through all of that again, but at various temperatures. And then you would make something called an Arrhenius plot. Which is the natural log of the rate constant versus 1 over the temperature. Make sure your temperature is in Kelvin. And this yields a straight line that hopefully will look a little familiar to you, because it is just a rearranged version of the Arrhenius equation that we had earlier in this video. So the straight line plot would have the equation, the natural log of K equals negative EA over R times 1 over T. I know this looks, why didn't I just put the T underneath? You'll see why in a second. Plus the natural log of A. Right, this is just a rearranged form of the Arrhenius equation. Now the reason that I separated that T out is that this looks like the form Y equals MX plus B, right? It's a straight line. And that means from my plot, the slope is going to be negative EA over R. Well, that's awfully convenient because R is a constant. So the slope of the line will give me the activation energy. And the intercept will give me the frequency factor. So this is really useful if you have a lot of data. That won't always be the case or I'm not going to necessarily ask you to deal with plotted data during something like an exam. But if you do this sort of 2-point form, we can take 2 points on this line and come up with a relationship between the rate constants and the temperature. So what this looks like is that the natural log of K2 over K1 equals a positive EA over R times 1 over T1 minus 1 over T2. So now if we know the rate constant and the activation energy, if we know the activation energy and the rate constant at one temperature, we can find the rate constant at any other temperature. So this is probably the form you will use most often, and certainly the form that you would use on an exam. I think there's some practice potentially in a PLTL. If that ends up not being the case, then you just won't need to use this full straight line form. You might need to use the 2-point form, or if you're given all of the other information, you might need to calculate the rate constant using the Arrhenius equation that we gave initially. So we have talked about using the frequency factor, but we haven't talked about why we have it or what it means. And it's all related to this model for how reactions go called the collision model. So our question is really, why is there a frequency factor? And what does it mean? So A, this frequency factor, just as a reminder, what it represents is the number of approaches to the activation barrier per unit time. So if you have two molecules that are trying to react with each other, not every approach has enough energy to overcome the barrier. And the molecules have to collide with the correct orientation. So we're going to draw a couple of pictures of what we need to understand for this. So in the end, kind of put a little summary sentence here, the reaction occurs after a sufficiently energetic and properly oriented collision. Okay, so I'm going to draw a picture of what this means and then kind of put it all together with a little summary about it. So what proper orientation means. Let's look at NaCl gas. I mean, technically our reaction is 2 NaCl gas turning into 2 NO gas plus Cl2 gas. But, right, we've got 2 NoCls. So NoCl plus NoCl turns into 2 NOs and a Cl2. So if my skeleton structure, I'm not going to draw a full Lewis structure for something like this, right? It's N connected to O connected to Cl. And I have 2 molecules of this. So if they're oriented this way, right? I have my 2 molecules. This one's moving in this direction. This one's moving toward it. If they run into each other with this orientation, this would not be effective. And that may not be immediately clear, but take a look at what we're trying to form. 2 NoCls, right? So NoCl, NoCl. But I need to form Cl2. I've got a Cl here and a Cl here. If I want the Cls to bond to each other, they need to run into each other in order to do that. So the reason that this isn't effective is that we need to make Cl2. So this will only be an effective collision if the Cls are close to each other. So let's take a look at what an effective setup might look like. And it could be any number of ways that they run into each other, but any way that they are lined up to form Cl2 would be an effective collision. So one example would be, say a molecule oriented this way and it's moving to the right. If whatever molecule is approaching it from the left has Cl pointed, so it will run into the other Cl, this will be an effective collision because my Cls will run into each other and then it will go on to make the product. So what this means in terms of the frequency factor and why this is included in our rate constant. K calculation is how I want to put this. I want to put an energy diagram up here again. Right, so I've got my reaction coordinate, and then this was energy. And let's just say, we can do, right, these are my reactants. We'll put my products at a higher energy this time, so you can see what that would look like. So my activation energy, right, is from the reactants up to the products. We can label a couple of things on here. Right, this value between the reactants and the products was my delta H reaction. The activation energy is from the reactants to the top of the hill. So look how big it is this time. It's always from the reactants to the top of the hill. This is my activation energy. So what the frequency factor is saying in our calculation of K, right? We just said that we have to have enough energy and the proper orientation. So we have all of our reactants down here, and they are, bouncing around in solution, bouncing around in the gas phase, whatever type of reaction it is. And you have a couple of the molecules that approach each other, and they go, but they don't have enough energy, so they don't get over the hill. And then you have them go again, and they have enough energy, but they don't have a proper orientation, so they don't get over the hill. So then you go again, and maybe that time they didn't also have enough energy, even if they had proper orientation. And we'll go one more time, and they have enough energy, but not proper orientation. And then finally, because I'm going to run out of colors and we should finish at some point, they go. They have enough energy, they have the proper orientation, and make it over the hill. So everything that's kind of collected in all of these arrows represents the frequency factor, because every single time the reactants try to get over the hill, they aren't going to make it, which is why we include this in our calculation of the rate constant.